This program is a presentation of UCTV for educational and non-commercial use only.
Good morning. All right, good job. I want to welcome you to Livermore and the Bankhead Theater, and thank you for coming to Science on Saturday, now in its third consecutive year here in the Bankhead. First, can I see if any students from the Pleasanton area? Any show of hands? Great. How about Tracy? How about Livermore High School? Granada High School? Great job. Glad to see you're here. Lawrence Livermore National Laboratory produces this science presentation with the help of our local educators. So big thank you to the Lawrence Livermore National Laboratory. Our topic today is the distant worlds, making images of other solar systems. We've all seen space movies and the visual special effects of planets and galaxies. The one that always impressed me was the movie Contact, where the TV transmission leaves Earth and the camera pulls away, and you're going past the planets, the stars, and the galaxies. Well, that's all Hollywood special effects, and today's speakers will talk about how real images of space are made with telescopes on Earth. Today's speakers are Dr. Bruce Macintosh, Dr. Lisa Poyneer, and Granada High teacher Tom Scheffler. Dr. Macintosh is an astronomer with the Lawrence Lab. He grew up in Canada and obtained his BSc in physics at the University of Toronto. He wanted to be a physicist until he realized physics was too complicated to explain at parties and switched to astronomy. He also has a PhD in astronomy from UCLA. Dr. Macintosh was part of a team that built laser guide star adaptive optics for the Shane telescope at Lick Observatory and the Keck telescope at Mauna Kea in Hawaii. Since then, he's used his adaptive optics to search for planets orbiting other stars and leads a project to build an advanced planet finding instrument for the Gemini Observatory. Dr. Lisa Poyneer has worked for the lab since 2001, developing groundbreaking technologies in the field of adaptive optics for astronomical telescopes. A lifelong nerd, Lisa loves finding ingenious solutions to complicated problems, especially if their Fourier transforms are involved. Lisa studied computer science and electrical engineering at MIT and won awards for being the top female student and the top engineering student at MIT. A 1999 Rhodes Scholar, Lisa had earned a BA in Modern History at Oxford University. Concurrently with her employment at the lab, she completed a PhD at UC Davis in 2007 and won the 2008 Marr Prize for the most distinguished doctoral dissertation at UC Davis. Mr. Scheffler received a Bachelor of Science degree in Physics and Applied Mathematics from Western Michigan State University in 1997, and a Master of Arts degree in Astronomy and Astrophysics from the University of California at Berkeley in the year 2000. While at Berkeley, he researched, analyzed, and cataloged Hubble Space Telescope images of galaxies, observational research involved in the detection and study of extrasolar planets, and discovered supernova 1998 DT while working at the Katzmann Automatic Imaging Telescope team. During his graduate studies, he fell in love with teaching and entered the teaching profession in 2000. Please welcome Bruce, Lisa, and Tom.
Thank you very much for the introduction. I'm Bruce Macintosh. As you said, I'm an astronomer from the Lawrence Livermore National Lab. And with my colleague Lisa Poyneer, we're going to talk about studying planets, not just the boring 9 planets we happen to know about in our solar system, but planets orbiting other stars. I'll start with the boring ones, explain a little bit about our solar system going back over a couple of thousand years, how we've come to understand the way our solar system is put together and our place in the universe. but then move on to the core of the talk, which is extrasolar planets, planets orbiting around other stars. When I was in high school, we knew about 9 planets. Pluto was a planet back then. Now astronomers actually know about 430, almost all of them not in our solar system, but going around other stars, including many of the stars you can see with your naked eye at night. I'll talk about how they're discovered, what we know, and the difference between what we know about these planets and the sort of NASA press releases or gorgeous pictures that you see in movies, and then what we'd like to know about them, more advanced techniques. And then Lisa will talk about the technology that enables that, telescopes, how they work, what their capabilities are, and a Livermore technology called adaptive optics. And then finally, I'll talk about our science result using this adaptive optics, the first real image of 3 planets going around another star. So this is the view of the universe that was held 2,000 years ago by Ptolemy. Back then, people thought the Earth was the center of the universe. It's a fairly obvious picture. There's the Earth, and there's everything else. And everything else, like the sun, the moon, the stars, the other planets, would all orbit around the Earth. And that's not a terrible conclusion to make. If you watch the sun, it goes up in the sky. You think it's moving, you think you're not. If you watch other planets, they go around not just over the course of the night, but over the course of a year. Planets will move to different locations with respect to the stars, with respect to the time of day. So the idea that the Earth was the center of the universe, given human egotism, was a fairly natural conclusion. In fact, if you know somebody with a large ego, you can think of them as having a Ptolemaic view of the universe, that they're the center and everything rotates around them. In this sort of simple picture, the Earth is the dot in the center, and you can see the sun goes around it, and other planets also go around the Earth. And that worked okay, except that if you watch the planets carefully over the course of a year, you see that sometimes they move backwards and forwards. Sometimes Mars goes to the east, sometimes it goes to the west. Sometimes Venus goes east, sometimes it goes to the west. And so to reproduce that, Ptolemy and his successors had to add more and more complicated paths for the planets, with the Earth holding still and all the others swooping around it. Instead, Copernicus realized you could make all that work if you put the sun at the center, and we sit on the Earth. And so sometimes we see Mars and Venus getting close to us, sometimes we see Mars and Venus getting further away, and everything moves in a nice regular circular or elliptical pattern, going out to the outer planets like Jupiter and Saturn. That Copernican view is really the first opportunity to start thinking of the Earth as not being special, that the Earth wasn't this unique thing in the center of the universe, but the universe was vastly bigger than anyone had realized. Kepler, a later astronomer, started writing down laws that explained how this worked mathematically. There were 3 laws. Roughly speaking, they said that planets move, and they move in elliptical, not exactly circles, but squished circles, orbiting around the sun. His second law was that when a planet gets closer to the sun, it moves faster, and we now understand that's because the sun's gravity is stronger the closer you get to it. And his third law was that the more distant a planet is, the longer it will take to go around the sun. And that's going to be important. I'll return to that as I talk about how we study our system and other solar systems. This view of the universe was very compelling to other scientists. It actually did a good job of predicting exactly where Mars would be on June 23rd, 1603. It wasn't that compelling to ordinary people, because to ordinary people it looks like it's all going around the Earth. And so there was a lack of a visual demonstration, something that could actually show you that the Earth wasn't really the center of the universe and that other things orbited each other. And that was actually provided by Galileo with one of the first telescopes, and Lisa will talk about how that happened. So this is roughly what they thought the solar system was like in 1600. There's about a total of 6 planets you can see with the naked eye: Mercury, Venus, Mars, Jupiter, and of course the Earth, which we can all see with the naked eye. This is what we think the solar system looks like now. There's 8 planets since they demoted Pluto, plus a couple of extra things we call dwarf planets. You'll notice that there's a difference between the different kinds of planets in our solar system. Close to the sun, there's little planets: Mercury, Venus, Earth, and Mars, and they're made pretty much out of rock. They're solid things you can stand on. Far from the sun, they're giant planets, hundreds of times bigger than the Earth. Jupiter weighs about 300 times what the Earth does. And they're mostly made not out of rock, but out of gas. They have little cores of solid material, but a huge gassy envelope of hydrogen and methane and other chemicals like that. And astronomers thought they understood that. When I went to graduate school, I was taught how we thought planets formed, and I was taught that they would always form in this way. We didn't know about any other planets orbiting other stars, but I was told by my professors when we did, they'd look just like our solar system. There'd be big giant planets at the edges, little rocky ones in the middle. And so we hadn't really finished getting away from this Ptolemaic view. We thought our solar system was the solar system, and everything else would have to look exactly like it. And that turns out not to be the case. Kepler's laws tell us about how long the planets go around the sun. Closer they are, the faster they go around. So Mercury takes a quarter of a year to go around the sun. Earth, everybody should know, takes 1 year to go around the sun. That's why we have seasons. Jupiter takes 12 years. Saturn takes 30. Neptune, out at the edge, takes 165 years to go around the sun as they follow these laws. So I'm going to try to set up an example to give you a sense of the scale of our solar system, and so that I can compare it to the other solar systems we've found. So if I wanted to do that in this room in a completely realistic way, if I wanted to fit a model of the solar system into this room, the sun would have to be this big, Earth would be about this big, Jupiter this big. It would be relatively hard for people to see. So I'm going to cheat. I'm going to make the planets much bigger than they ought to be and the sun much bigger than they ought to be, if I could get the sun to come on. There we go. The sun is a relatively happy star. It has planets. The ratios of the sizes are all going to be right. So Jupiter will be the right size compared to the sun, and the ratios of the distances will be right, but the solar system is going to be squished up. So I can get my inner solar system to come out. By comparison to the sun, that would be Venus and Mercury, and then Earth and Mars, we'll put over on the other side. So they're a lot smaller than the sun is, and they're relatively close. Yeah, it's a good arrangement. Let's see. The giant planets, on the other hand, are way out in the outer parts of the solar system. So I think I have somebody ready to hand out the giant planets. Okay. So Jupiter goes in roughly the first row. So if you can find somebody in the first row who's willing to stand up and hold up Jupiter, the big one, that would be good. Any volunteers? All right. Saturn goes into the third row. I'd actually rather have Jupiter over on this side of the room. We're going to have some other planets on the other side of the room. So you guys will get your chance on this side. So hand Jupiter over in this general direction to somebody. Saturn in the third, thank you. Uranus goes in the ninth row. You can go on up. Do you have the objects for Uranus in the box? And then Neptune goes all the way at the back. Let me move Jupiter over here for purposes of this experiment. Thank you. We'll give you another planet later, maybe. All right. So first, you notice solar system's mostly empty space, and second, as I said, there's this hierarchy. There's little rocky planets close in, which is nice because we want to live on a rocky planet. There's big giant planets in the outer parts of the solar system. After people got all this sorted out, they wanted to ask, were there other planets? And even around other stars. Even 1,000 years ago, a philosopher called Albertus Magnus was saying this is one of the most important questions in science. And I happen to think it still is. Is our solar system unique, or are there other ones out there like it? And so people started searching for them. The problem is it's hard. Planets are tiny and stars are bright, and you can't easily see a planet near a star. All you can really see if you look at it, even with a good telescope, is the stars. What astronomers first took advantage of was gravity and motion. The Earth, as we all know, orbits around the sun, but the sun actually orbits around the Earth a little bit. Newton worked out that if the sun's gravity pulls on the Earth's gravity has to pull back on the sun. And so they both move around a point called the center of mass in between them. The Earth does a lot more moving because it's small. The sun moves only a little bit. But the sun does wobble in response to the gravity of the Earth, the gravity of Jupiter, the gravity of everything else in the solar system. And even if you couldn't see the planet, but if you did see the wobble, you could do a pretty good job of guessing there was a planet there. And that's how the first planets orbiting other stars were discovered. The next question is, how do you tell that it's wobbling? The way we do that is using the Doppler Shift, which people are relatively familiar with. You all know what the Doppler Shift for sound. As something's moving towards you, it gets higher pitched. Moves away from you, it gets lower pitched. Exactly the same thing happens with light, except light doesn't have a pitch. But if something's moving towards you fast enough, its light gets a little bit bluer. It gets shifted. If something's moving away from you fast enough, its light gets a little bit redder. And by measuring that change, we can tell whether an object is moving towards us or away from us. And so we apply that to stars. When astronomers started finding planets around other stars, NASA made all these gorgeous pictures to go with the press releases of, look, we can see huge giant planets. It's got a moon that's evaporating because it's so close to its star. Of course, that's nothing like what we actually see. And in fact, when we study these systems, we don't see anything. All we see is that gravity, that little wobble of the star. It tells us maybe there's a planet there, not much else. So the real astronomy results are not this. They're this, lines on graphs, which is, even I actually have to say, is kind of boring. But was the first clue that there were planets orbiting other stars. Imagine that we're the Earth, and we're down on the stage looking up at the star, and the star is wobbling because the planet's going around it. The star will come towards us, away from us, towards us, away from us, towards us, away from us as the planet orbits it. And the light, the spectrum at the bottom, will get a little bit bluer, a little bit redder, a little bit bluer, a little bit redder as the planet wobbles around. The graphs are a plot of that. Watching a star over the course of several months, astronomers measured its velocity and found sometimes it was moving about 50 meters per second closer to us, sometimes it was moving about 50 meters per second away from us. Tiny amounts, and now they can measure down to as small as 1 meter per second. But that little bit of motion, told them that there had to be something making the star move, and that something was a planet. That tells us things about the system, but not everything. One thing it does, you can measure, is how long it takes to go around. So it took these first planets discovered went around the star in 4 days. So can anybody guess, given that, where the planet is going to be compared to the star, given what I told you about Kepler's laws? Going to be close to the star, far away from the star? Close, right. And in fact, it's going to be extremely close. That's going around a lot faster than the planets do in our solar system. Mercury goes around in a quarter of a year. This planet goes around in 4 days, and so it's pretty much grazing the surface of its star. I'll get my other star to come in. So this is Upsilon Andromeda. It's less happy because it has less interesting planets than our solar system does, but it's very brightly colored. I think they want you to stand where it's pretty well lit, so this is a good location for the light. Upsilon Andromeda, we now know, has about 3 planets. We can get them to come in. And they're over here. So one of them, again, is a giant Jupiter-like planet. One of them is a little bit smaller than Jupiter, and one of them is kind of in between. The giant Jupiter one is extremely close to it. This one's about here. We'll put you over on the other side, though we don't actually know which side. Yeah, come over here just so we got a little more room, which side any of them are on. And so you can see with my volunteers here how different this solar system is than our own. In our solar system, can I have the outer planets of our solar system stand back up? So Jupiter and Saturn and Neptune and Uranus. All the big guys are out in the outer parts of the solar system. The little ones are in the center, which is sort of where we think they actually belong. In these systems, it was a tremendous surprise to astronomers to discover giant planets close to the solar system. They couldn't see, the techniques they used aren't sensitive enough to tell if there was an Earth. They could only see the giant planets. But with those techniques, you can actually be pretty sure there isn't an Earth. We got Earth here. I'm just going to move Earth over here. If you put Earth in the location it would be in this solar system, it would be about here. And these planets would, maybe not hit it, but they'd probably get pretty damn close to it and knock it out of the solar system. So all these other solar systems don't actually have room in them for an Earth or anything like it. They just have giant planets in basically the wrong part of the solar system. We can tell, I said, that these planets are as big as Jupiter or bigger, and we tell that again from the Doppler shift. The bigger a planet is, the stronger its gravity is going to be, and the more it's going to make the star wobble compared to a small planet. Over 400 extrasolar planets have been discovered so far, almost all of them using this Doppler technique, which is very powerful. It's told us a lot about other solar systems, but it hasn't really found a system exactly like our own. We guess that these planets are like Jupiter. We guess that they're mostly hydrogen, with little rocky cores, but we don't know that. All we know is how much they weigh. They occasionally fall to the ground. Not a lot else about their properties. There are a couple of systems for which we can use one other technique. I can borrow one of the giant planets again. Let's take the close-in one like this. Every so often, occasionally, for some stars, the planet will pass in front of the star. When it does that, the star will get a little bit dimmer because the planet's opaque. It blocks the light of the star. Then it'll get brighter, it'll get dimmer. It doesn't happen very often. If this guy were orbiting like this, orbited around like that, you wouldn't see any dimming. It's only if it happens to line up exactly between the Earth and the sun and the star. That only happens for about 1 planet in 100 or less. But there are enough where it takes place that we can measure a little bit more the diameter of the planet. You can actually do this kind of observation with a tiny telescope because all you're looking for is a change in the brightness of the star. And in fact, somebody discovered one of these from Pleasanton with a telescope in his backyard by looking at a star, and he saw that it got about 2% dimmer and that was due to a planet passing in front of it. You can also do it with a large telescope. NASA has a space mission called Kepler, which is sensitive enough that maybe it could see an Earth-sized planet producing this dimming sometime over the next 5 years or so. So that's a good technique. It tells us a little bit more. It still doesn't give us pictures like this because you're not seeing the planet. You're just seeing it get a little dimmer. But at least tells you how big the planet is because you can calculate exactly how much dimmer it got and what fraction of it was blocked out. What we'd really like to do is actually see the planets, and that's going to be very hard. So we can ask our volunteers, we can thank them for standing up and holding the planets. We'd like to make a picture like this. We'd like to actually see, maybe not a giant beach ball, but a star and a little planet dot to it. But that's nearly impossible. The sun is 1 billion times brighter than Jupiter is, as seen from outside our solar system, and the metaphor that I'm required by astronomer law to use is that looking next to a searchlight in order to see a firefly. That's hard, but we're working on technologies, which Lisa will now talk about, that potentially allow us to see this little tiny dot hidden in the glare of the star.
So good morning. Okay, so I'm going to be talking about the engineering. In particular, when I was a kid, I wanted to be an astronomer. That was really interesting to me. And then when I got to college, I took a class in physics, and I decided I didn't want to be a physicist either. So no offense to any physicists in the audience. What I really like doing, actually, I'm an electrical engineer, and I do signal processing. But it's very exciting for me to be able to work on building the instrumentation that makes this kind of science possible. And Livermore Lab has a world-class program in adaptive optics. And it turns out there's a lot of technology that is behind those pretty pictures that you might see in the New York Times. So I'm going to be discussing two major points about that technology. The first one is, why do we use a telescope? I'm going to be talking about telescopes and how they help us. And then I'll be talking about this technology called adaptive optics. So as Bruce discussed earlier, there are these models we had for what the solar system was like. And 400 years ago, Galileo took one of the first telescopes and looked up at Jupiter. And through his telescope, he saw that there were some bright points of light next to Jupiter. And he recognized through observations on the same night and on consecutive nights that those bright points were moving. And he was able to figure out that they actually were moving as if they orbited Jupiter. And here you see an animation of those spots, and it fades into what we actually know Jupiter and its Galilean satellites look like. So this was 400 years ago, and he was the first person to really use a telescope to look at the heavens. And he wrote a book, a short book. It's 15 pages. It was called The Starry Messenger, and it is a top contender for maybe the best scientific paper that has ever been written. It was just by himself. And he looked at a lot of things. But of all the things he saw, he, in his own opinion, thought that this discovery of the satellites around Jupiter surpassed all wonders that he was able to find. And the reason for this is in the community, when they started thinking about the Ptolemaic system, that made a lot of sense intuitively. Well, obviously, everything rotates around us. The Copernican system was a bit harder to accept, and in particular because everything orbited the sun, but the moon orbited the Earth. All right, so how do you explain that? And the fact that he was able to look out and see that 4 bodies were orbiting around Jupiter, he thought would quiet the doubts of those who were disturbed by this. It was an example that not only can Jupiter travel around the sun, but other objects can orbit around Jupiter itself. So this really set off a revolution in the way that we think about the universe. And Galileo, as I said, did this 400 years ago. And he did this with a very small telescope. He actually did this with a 2-inch telescope. Right? And so this is about, you could buy this actually for about $20. There's an organization, galileoscope.org. You can order one and put it together yourself. It's a replica of the telescope that he used. And the power of a telescope is set by the size of its lens or mirror. And in this case, or as the case with binoculars, it's about 2 inches. Right? The lens at the front is about 2 inches, and that sets the power. Right, so I said you can see Jupiter's up right now. It's the really bright object that you see in the west right after sunset. In your backyard, you can, through a 2-inch telescope, see those moons orbiting it. If you get really interested in this, you can upgrade. You can buy an 8-inch telescope. You see 8 inches is the width there in the front, with a woman looking through the finder. And so for about $1,000 new, you can buy an 8-inch telescope. And despite the fact that we have a lot of light pollution here, you can see a tremendous amount of stuff from your backyard. And so this is like the next step up. Going even further, we're going into the realm of professional astronomers. We get to the 36-inch Great Refractor at Lick. So Lick Observatory is in the hills east of San Jose. I highly recommend going up there to visit. And they have this beautiful telescope, and you can see in this photo that there's a man standing down there at the bottom. Right? This is a gigantic telescope, just like when you picture a pirate using, and the lens that is at the front end is 1 meter across. It's 36 inches. And when this was built 100 years ago, this was the largest telescope in the world. And you can look through this. I've done it myself. And in the summer, you can drive up to Lick, and they have programs, and you can look through this. It's just phenomenal, the amount of detail that you can see. So this was state-of-the-art 100 years ago. Nowadays, professional astronomers use telescopes 8 meters and larger. Right? So 8 meters is 26 feet. And you see in this photograph that white blob in the center. There's actually a person in a bunny suit, and they are working on polishing this mirror. Right? So this mirror would fit on one side of a volleyball court. It's enormous. And this is what professional astronomers use. They use 8 and 10 meter class mirrors to do their observations. So we've been talking about the different sizes, and that has a big impact on what you can see. Right, so I mentioned you can go in your backyard with your 2-inch Galileo scope and look up, and this is an example of what you might see. Can anyone tell me what we're looking at? It's Saturn, right? And you can identify it. You mean you know what to look for, right? But you can clearly see that there's some structure there. You can see its rings, right? So you could view this through a 2-inch telescope. What an astronomer would record through an 8-meter telescope is something more like this. This is the theoretical limit for an 8-meter telescope. And it's just incredible how much detail you can see. You can see the rings, and there are hundreds of separate rings in the system, and you can see detail in the cloud structure. Right? And this is the kind of detail you might actually expect to see with a space probe, something that's actually gone and traveled to Saturn and taken pictures of it. And so this is the theoretical performance we might get from one of these giant telescopes. Right, so I've talked a lot about the detail, and it's bigger, but this is a very important point. Bigger is not always better. What you want is more detail. And this should be very familiar to you from digital images. Right? You have a friend who texts you a photo, you transfer it back to your computer, and you blow it up, and it looks terrible. It's just a bunch of pixels. All right. That's because it was acquired at low resolution. So you see here an image of an iPod, and as you blow it up and you zoom in, you can't read what the artist is, right? Because the original image was too small. It had too little information in it. So what we want is not just a big picture of Saturn, for example, or another solar system. We want a detail in that image. So we're going to step back through those images of Saturn to show you the real impact of this telescope size and why astronomers want large telescopes. So this is the 8-meter image. We're going to go down to the 36 or the 1-meter image from a Lick-like telescope. So we've lost a bit of detail. It's still really great. Now let's go to an 8-inch telescope you could use in your backyard. So still quite nice. You can see the Cassini division, and you can tell that there are bands of clouds. And this finally is that 2-inch image. All right? And this is just blown up from that first image I showed you a few minutes ago. Right? Your eye instantly recognized it was Saturn. You knew what to look for. And you can tell that there's something on the side. And Galileo did look at Saturn as well. And he was quite confused at the start as to what those blobs on each side were. He thought they might also be moons. Right? So these big telescopes give us wonderful magnification, but they also give us improved resolution. And the final reason we like these large telescopes is the amount of light that they allow us to gather. Right, the size of the aperture, I've been quoting these numbers, right? The bigger those numbers are, the more light can come in. Right? And just as here you're in a fairly dark room, right? And if you could look in a mirror, you would see your pupil is dilated. It's gotten bigger. And if you're here or you're at the movies, your eye adjusts, and then you walk outside. It's a bright sunny day, right? And it hurts. Light is flooding in your eye. And the response, physiologically, is your iris will narrow down your pupil to allow less light to enter. And so it's the exact same thing with the telescope. The bigger we make the aperture, the more light is going to come in. And in fact, the difference between your eye and an 8-meter telescope is a factor of 16 million. Right? So that's like the difference between looking at something for a second or staring at it for 6 months. Right? And so that's why astronomers like these giant telescopes, is they enable us to receive lots of light so we can observe things that otherwise would be invisible because they're too faint. So to summarize, I think there are 3 big advantages to using telescopes, and in particular for our application. So these advantages are the magnification. Right? We can see things that are far away, and they appear bigger. Right? So we can look for another solar system. It's really, really far away. So we need magnification. We also need resolution. Right? Bruce talked about these planets. They're smaller than the star, sometimes a lot smaller, and they're very close. Right? And so in order to see that, we need detail. We don't want to resolve just the W on the top of that eye chart. We want to resolve the letters on the bottom, on the bottom there. And finally, light. And again, Bruce used the analogy of a firefly next to a searchlight. The planet's very faint, so we want to get a lot of light in. Okay. So, as I said, with planets, they're very, very far away, and they're very close to their star. That's resolution. And because they're very faint, we need lots of light. So I've been showing you some stuff, and I've actually been lying to you a bit. All right, I put up those pictures of Saturn. I said, look at this 8-meter telescope. It's fantastic. It's actually not. That was a theoretical limit, and no Earth-based observatory is going to see something like that. And the reason it's not is the Earth's atmosphere. So here we have 2 movies. These were both taken through an 8-inch telescope on a lab project. On the left is 580, and on the right is a barn up near Morgan Territory. And you can see as these play, these images are being distorted. Around the barn, you can see waves almost moving across it. And this is just the mirage effect. Right? We all know it's really hot here in the summer. And the heat coming off a road, when you look through it, you see distorted images. You see mirages. Right? The exact same thing happens if you're an astronomer and you're looking up at a star. Right? Twinkle, twinkle, little star. The atmosphere causes distortions when you look up, just as when you look out. So these stars are trillions of miles away from us. We're talking tens to hundreds of light years. And the star, so it's very far away, and our light travels all that way to us. And we're sitting there waiting for it with our telescope. And it just, the last little bit, the last couple dozen miles, that light encounters the atmosphere. And that's where all the trouble happens. And here you can picture these kind of blue blobs, right? The atmosphere is thick. And it has regions in it that have different temperature and pressure. And as the wind blows those, they kind of go across over the telescope, and they change with time, and the light here symbolized by this red arrow moves, is aberrated as it passes through the atmosphere. Right? And this process significantly degrades the image quality. So this was a nice image of Saturn that I showed you. I said, oh, look how fantastic. This is great. In reality, this is what you would see. Right? All that detail's gone. And this is the type of observation you would take from this giant telescope. Right? This is what you'd actually see. And in fact, for comparison, this is the 8-inch telescope image I showed you earlier. They're almost exactly the same in terms of resolution. Right? And so there's a factor of 40 difference and a factor of a lot of millions of dollars. Right? A large telescope would be, tens to $100 million to build, and you can buy an 8-inch one for $1,000, right? And they have about the same resolution. This is how bad the problem of the atmosphere is. Right? So we want to fix this problem, and we've been able to. Does anyone have any ideas about what we might do to avoid this problem? Anyone? You can just shout it out if you want. Okay, actually, maybe I'll call on someone. That was like 5 answers. Anyone? Yeah. Oh, great. You've been paying attention. Anything else? We'll get to that in just a moment. Anyone else have a good idea how you could avoid this problem? Yeah. Yeah, so if we put it in space, the light never goes through the atmosphere. So this is, for instance, the Hubble, probably the most well-known telescope ever. Right? It's up in space. But that's very expensive. We're not talking $10 million. We're talking $1 billion, right? And the telescopes are smaller, right? One other thing, besides adaptive optics, I have one other thing we could try. Does anyone want to hazard a guess? Yeah. Yeah, so that's what we're going to be doing. So he mentioned moving the mirror. That's adaptive optics. So how many people watch 24? Right? Yeah, so you know what happens? Jack needs some surveillance footage. He's looking for a license plate. He says, Chloe, fix that up. Bam, all of a sudden you can see all the detail, right? This image processing. And you can take degraded images and improve them after the fact. And this is an example from a lab project. On the left is an image taken at about 1 kilometer of a man, and it's all blurry. And we take a series of those images, and we post-process them, and we can produce the image on the right. You can see that this man is wearing glasses. You can tell what kind of clothing he's wearing. You might even do facial recognition on him, right? So we can do improvement after the fact. But But what turns out, what we really want to do is build an adaptive optics system. And as was mentioned, we have a mirror in this system, right? This is a system with a computer and optical components. It's about the size of a person there. You can see those engineers working on it. And we're going to put this on the telescope. Okay. So now we're going to go on to our demo, which Tom and Garrett are going to help us with. And we're going to be using a demo with a laser pointer. So as they get set up, I'm going to explain the basics of what we're doing. And we're using a laser pointer. I just want to mention we're actually using a class 2, so it's not an eye hazard. But do not go down to Fry's and buy a class 3 green laser pointer and shine it towards your face, right? You don't want to play around with these. So we're going to set up the laser pointer there. And that light is going to be reflected off a mirror. And we're going to then aim it at a target. There we go. Okay, so you can see what they're getting things set up. Okay. Okay, so if we could switch back to the slide display, I have a target. Thank you very much. Okay, so there we go. So you can see the red laser spot there centered on the target. So this is our setup. We have this laser that we can control, and it's going off a mirror. So the first concept we want to illustrate is this idea about resolution. Right? So right now, while the laser is being held steady, we see that spot of light, and it's on 1 square. That's a pixel. Or you could think about that as being a photoreceptor in your eye. Right? It's going to give us a very sharp image. But as soon as something like the atmosphere starts aberrating the light, the spot will move around. And you can see here, we're losing it a bit. There we go. Are we off the edge of the mirror? No? Okay. So as you can see, as this red spot is moving around, there we go, it actually hits many pixels, right? And it makes it dimmer. So this spreads it out, and it blurs the resolution. And so instead of a very fine point for the star, we would see a big blob, right? So let's go back, and now we're going to demonstrate how we could fix that. So the first thing is if the spot moves off target, like right there, we can measure that it's moved off. We can figure out, oh, it's up towards about 11 o'clock by about 2 squares. And then we can move the mirror, and we can move the mirror to steer it back in. So if you can see what they're doing over there, first we can move the spot off target by adjusting it, and then we can figure out where it's gone, and then Garrett will adjust the mirror to go back. All right, so this is what adaptive optics does. We take a measurement, and then we use our mirror to correct for the aberration. Great, thank you very much. Let's give them a hand, actually. It's taken us a while to figure out how to do that. Okay. All right. Okay. So this was a simple example, and actually you can buy systems that essentially do this for your backyard telescope. They cost about $1,000. But for adaptive optics, we actually have a much more complicated problem. So what I'm going to be talking about here, I did my PhD dissertation on just one small little bit of this. There's a lot of detail in here, and you're welcome to ask questions about it later. I just want to go over the basic concept of what we're doing. We now actually have several different rays of light coming in from the star, and they are going to be, oh, there it goes. We are going to have all of those rays of light converging on our target. That is our image of the star. Right? So the light comes from the star, goes off the mirror, and hits the target. When we have an aberration from the Earth's atmosphere, as the light goes through, it's skewed, right? And when it goes and reflects off the mirror to the target, it's now off. And you can see how these rays are now no longer converging. They are actually crossed up. And this is why we actually have a degraded image. Right? The light is being spread out. It's not concentrated. So we want to fix this, and we do this by adjusting the mirror, as was mentioned earlier. And in particular, we adjust the surface of a mirror. So if you've gone to, say, the county fair, or you've gone to a fun house, you've seen these funhouse mirrors, and they actually have a warped surface. And your reflection looks really funny in them because of that. we have something very similar in adaptive optics. We have what's called a deformable mirror. And in this schematic, we have a thin, flexible mirror surface there on top in gray, and it is attached to a base via these posts, which are in magenta and the blue dots. And we can, through, for example, electrostatics, adjust the height. And we can make the mirror go up or go down. And by doing that, we actually adjust it by about 2 microns, which is 1/50th of the width of one of your hairs. Right? These are very small, precise devices. And we actually have over here, let me walk over to it, we have a deformable mirror. This one is actually fairly large. This is about 1.5 inches, and it's a hexagon here. And we are going to simply move this surface, as I said, by incredibly small amounts. But that's going to be enough to get the job done. So schematically, what's going to happen in our cartoon here is the light is now going to come in. It's aberrated. It's going to hit the mirror, and we're going to adjust the surface of that mirror. And in this case, we're going to lower it, you can see there, and the resulting light ray heads where it's supposed to. And then we have another one come in. In this case, we're going to actually raise the surface, and it's going to cause the light to head right to the target. And our final one, again, we're going to lower the surface. And now we've made all the light go where it's supposed to, and we've cleaned the image up. So the pictures I showed you of Saturn were processed by me in my computer. They are not actual pictures taken from a large telescope. This is actual science results right now. These are some results for Neptune, and this was taken with the Keck telescope. So the first image here is of Neptune without adaptive optics. This is the blurry case. And you can see, you can tell it's a planet. All right, it's about 20 pixels across. And you can see some variation in this false color image. Right, you see a bright red spot. But other than that, who knows? When you turn on the adaptive optics system, this is the kind of image that you get. It's taken at a slightly different time, but all that cloud structure just pops right out. And you can see a bright spot. You can see these little patches, bands of clouds. Right? This is actual adaptive optics in action. And we are working now on building systems that are about 10 times better looking for planets. So before I hand it back to Bruce to show us some much more exciting science results than just this example, I want to summarize what we've talked about. All right, so we've been covering telescopes and adaptive optics. All right, so telescopes, especially large ones, allow us to see very small and faint objects, namely planets. However, the Earth's atmosphere substantially degrades the performance of these large telescopes. And so we can use adaptive optics in a process of measuring and correcting these distortions to get back that image quality. Okay, so let's go back to Bruce. Go.
Thank Lisa for explaining that, and more importantly, for building all the technology that we actually use to do these observations. And so I'm going to talk finally about the science we're doing with this technology, studying planets. As I said, we know about hundreds of planets, but only as wobbles on a graph as their star moves around. And our group has worked and succeeded about 1.5 years ago in making the first images where we can actually see the planet separate from the star. We did this using the 10-meter Keck telescope in Hawaii. One of the good things about being an astronomer is you get to go to Hawaii about 3 or 4 times a year. One of the bad things about being an astronomer is when you go to Hawaii, you spend all your time 40 miles away from the beach, with 3 of those miles being straight up on the top of a volcano. But it's still a very beautiful place to work. It's one of the best parts of the job. The Keck telescope, which belongs to University of California and Caltech, is actually the biggest optical telescope in the world. And it's a little different than the telescopes Lisa showed you in that its main mirror is hexagonal. It's built up out of 36 individual hexagonal pieces of glass, which made it much easier to manufacture, but will have an effect on the images that I'm going to show you. The second thing we do is we look not just for ordinary planets, but for young planets. Jupiter, as I said earlier, is about 1 billion times fainter than the Sun, and that's enough fainter that even with the adaptive optics, even with the biggest telescope, we couldn't quite see Jupiter, let alone Earth, which is 10 billion times fainter than the Sun. And so we cheat a little bit by looking for planets when they're young. Planets formed around the Sun in a disk of gas and dust, and when that happened, a lot of energy was released. And so a newly born version of Jupiter is about 3,000 degrees, and it's glowing, much brighter than Jupiter is now. As it gets older, it cools down to 1,500 to 500 degrees, but only now, when it's 4.5 billion years old, does Jupiter get down to really cold temperatures and only reflect light. So we're looking at stars that we know are young, that are 10 million, 30 million, 100 million years old, because we think that means their planets will be bright and that we'll be able to see them more easily. The second problem we have is telling the difference between a planet and a star. If you look at a star, big bright star, and you see a little faint spot next to it with all this technology, you might be lucky. It might be a planet. It's faint because it's small. But it might actually just be another star and be faint because it's far away. When I started this process about 10 years ago, one of the first stars we looked at, we did in fact see a little faint smudge. The big black and white blotch on the left side is the star, and I'll explain a little bit later about why it's blotchy. The little circled smudge, we thought maybe it was a planet. But then we did the follow-up observations, and we discovered, in fact, it was a star. So we looked at another star and found next to it a thing. Maybe it's a planet. No, it was a background star. Found another background star. Found another background star. Another background star. Found 3 background stars at once, so we saved a lot of time in that observation. And another background star. Over the course of 10 years, we looked at about 200 stars, and we didn't succeed in finding any planets in our first set of observations. I, as part of this, worked with a very smart, younger, more enthusiastic postdoctoral researcher who realized part of what we needed to be able to do was to look closer to the stars. You see these big blobby patterns of light as we look at the star. Even with the adaptive optics, the light from the star doesn't come to a perfect focus. Some of it gets scattered by the mirror of the telescope, by lenses in the camera, by things like that. Just like a lens flare. If you take a picture looking too close to the sun, which you're not supposed to do with your camera, you'll notice there's a big glare and rays and blobs of light. Those blobs of light aren't really there, of course, but they're light from the sun that's bouncing off of the lenses in your camera. The same thing happens with the telescope and gives us this big, complicated pattern of light. So in this image, there actually is a planet. Can anybody see it? Tell me roughly. Can you tell me roughly where it is, like 9 o'clock, 3 o'clock? 10 o'clock. That's good. In this image, there's actually 3 planets. Can anybody see a second one or a third one? And the answer is almost certainly no. We're going to take advantage of the way the telescope works to tell the difference between the planet and the streaks. What we're going to take advantage of is the fact that the telescope is attached to the Earth, and the Earth is rotating, and so to follow the stars, the telescope itself has to rotate the other way. So over the course of a night, as a telescope watches a star, it's going to rotate around. The planet and the star will stay fixed because they're up there in the sky. They're not really moving. All of this glare, this hexagonal pattern of light, is attached to the telescope, and it is going to rotate. And so you can see the one planet at 10 o'clock really easily. Can anybody now see a second planet? It's about 2 o'clock, right? So you can tell because it's staying still. It's actually real. It's not an artifact. The third one you won't be able to see easily, but we wrote software that takes those images and looks for things that aren't moving. And as time goes on and it builds up a more sensitive image, you can just barely see down at the bottom, excuse me, back too far, the third planet in the system. So my postdoctoral researcher found these. He called me up. He said, I found a planet. I said, no, you found a background star. He said, then he called up and said, I found 2 planets. He said, no, definitely 2. We would not be that lucky. There has to be a background star. By the time he said he found 3, I thought he was crazy. But we did the observations afterwards, and these turned out not to be stars. These really, in fact, are planets. There's a pseudo-color image of them. The big blob in the center is still the star, which doesn't go perfectly away. The star they're orbiting has the rather boring name of HR 8799. It's just barely too faint to see with your naked eye, although it's bright enough that your cat could see it with its naked eye because cats' eyes are more sensitive than ours, but cats don't look at stars much. The planets, to my great disappointment, when you discover a planet, you're not allowed to name it. When you discover new planets these days, they just get serial numbers, and so these are HR 8799b and C and D. But we still found 3. It was still a fairly major result. It actually made front page of the New York Times about 1.5 years ago, together with another group that found a planet orbiting a star using the Hubble telescope, and people made comic strips making fun of us, which is what I consider to be a major level of scientific success. Compared to our system, this is now not like the Doppler systems where the giant planets are enclosed. This actually looks a lot like our solar system. We found 3 giant planets, and they were not in the center, but they're out in the edges where we think giant planets belong. The star is actually a little bit bigger than our sun, about 50% bigger, and as I said, it's very young. We picked it because we knew it was young, and so its planets ought to be detectable. And now, because we can see the planets directly, we can study their light, and we can tell things about what they're made out of. The outermost planet is about 7 times the mass of Jupiter, and we can tell from the color of the light coming from it that its atmosphere is mostly methane, carbon monoxide, water vapor, and hydrogen, and that it's hot, that it's about 1,200 degrees. The next planet in is about 1,500 degrees, and the innermost, again, about 1,500 degrees and 10 times the size of Jupiter. If we did the demonstration of putting them in this room, they would all be out in the back rows where giant planets are supposed to be. We're not sensitive enough to see an Earth. With the telescopes we have now, we couldn't see an Earth-like planet. But the difference between this system and the Doppler systems is there's room for an Earth. We don't see any giant planets going around in the center, and so potentially you could fit an Earth-like planet in the middle where we couldn't see it yet of this solar system. We can study their orbits. We've only looked at them for a couple of years, and actually a disadvantage of this system is it takes about 300 years for it to go around the star. But even with that couple of years measurements, we can try to predict where their orbits are going to go in the center. These are a couple of different predictions based on exactly where we measured the planets were over the course of the 2 or 3 years of motion. And we can even make predictions about how they're going to interact. These are very big planets. Their gravity is very strong, and they'll tug on each other. And that tugging will cause their orbits to distort. And in some cases, like the one on the left, they might actually end up passing too close to each other. And we've run 10,000 computer simulations of this system, and in 9,999 of them, the planets end up passing so close that one of them gets flung out of the solar system in about 10 million years or so, and only in one is the system going to last forever. In the future, I said we can't see Earths, we'd like to, and there's a couple of approaches being taken to that. One is building bigger telescopes. So this is a sketch of something called the 30-meter telescope. Can anybody guess how big its mirror is going to be? Right. It's designed by astronomers at University of California and Caltech. It's really the Your Name Here telescope because they're looking for someone extremely rich willing to donate enough money to build it, at which point it will be named the Gordon Moore or Bill Gates or whatever telescope. And it will be enormous. You can see next to it the 5-meter telescope at Palomar and a truck, giving you a sense of the scale of this instrument. That would be powerful enough, still maybe not quite to see Earths, but to see a planet maybe twice the size of Earth if it was going around one of the closest stars, and start to measure its composition. If you could see a planet, just like we did for the giant ones, we could figure out what its atmosphere is made out of, and maybe we'd see oxygen, maybe we'd see water vapor, maybe we'd see ozone, maybe we'd even see chlorophyll and see some evidence that there's life on it. To really see a planet exactly as small as Earth would take a telescope in space, and so groups working with NASA are designing that. Even in space, you have this problem with the lens flare, with the glare from the starlight. One of the cleverest ideas people have come up with to deal with that is to have 2 spacecraft. One of them on the right is a telescope, and it looks at the planet and the star. Another one in the middle is basically a giant umbrella in space, and it would unfold and move so that it blocks the star, but that the planet is just barely visible around the edge of it. And that actually could let you see a planet, even as small as Earth, around maybe the 100 nearest stars or so. And in simulations, it would produce images like this, where the little dot in the center is the star, almost completely blocked by the giant space umbrella. The dot above it is Venus, and the dot to the left of it is Earth, and potentially a blue thing with life on it. So that's where we're going to stop.
Okay.
I'd also like to ask our solar system volunteers to come out and thank them for holding up.
Hey.
All time.